So, hello everyone. Next, we'll go through the concept of compound cylinders. So, in this particular video, we'll be going through only the theory part of the compound cylinders. So, coming to the theory part of compound cylinder. So, actually, according to according to Lame's equation, which we had used previously in the cylinders and all. So according to Lame's equation, this is the expression for thickness of the cylinder, and it is given in the design data handbook, Mahadevan and Balavir Reddy data handbook, in equation number 7.11g. This is the expression for the thickness of the cylinder, right? So observe this equation. Observe this equation. So here, if you note in the denominator, here, if the internal pressure acting on the cylinder is greater than the allowable stress of the cylinder, that is, if internal pressure Pi is greater than the allowable stress of a cylinder sigma T, then what will happen? If this is smaller and this is larger, then the denominator will have a negative value. Then the denominator will have a negative value, and if you take the root of this particular negative value, then what you get is an imaginary value, right? So if Pi is greater than sigma T, then denominator it will be a negative value, and if you take a root, it will be an imaginary value. So directly the thickness will become an imaginary value in case the internal pressure acting on the cylinder is greater than the allowable stress of a cylinder. And also it is directly indicating that for any material, no matter what the thickness of the cylinder is, the cylinder itself will result in failure if such a condition comes into picture, right? If such a condition comes into picture, with thickness negative, the cylinder will undergo failure. And if such conditions are there, then it will be basically impossible to design the cylinder itself to withstand the internal pressure either equal to or greater than the allowable working stress. And these types of difficulties can actually be overcome by inducing some kind of initial compressive stress on the wall of the cylindrical shell. By inducing some compressive stresses on the cylindrical shell wall. Okay, basically it is nothing but pre-stressing the cylinder. So that is we give preloading to the bearings and all. So similarly here in cylinders we will be giving pre-stress before the actual operation. And how to pre-stress, right? How to provide such types of pre-stress, that is inducing certain compressive stresses on the wall of the cylinder. So this can be achieved by two different methods. One is using compound cylindrical shells. That is what we are going to use. And one more concept is the using the theory of plasticity. And that particular theory will not be discussing here anyway. So we'll be concentrating on the first option, that is the usage of a compound cylindrical shell. So as you can see here, this is a compound cylindrical shell. This is an example for the compound cylindrical shell. As you can see in this particular figure, there is an outer cylinder and an inner cylinder. If you observe well, this is the outer cylinder and this is the inner cylinder, right? The outer cylinder has some amount of thickness. The outer cylinder has some amount of thickness. So outer cylinder has an outer diameter as well as an inner diameter, right? So this is the outer diameter of the outer cylinder, and here comes the inner diameter of the outer cylinder, right? And this is the inner cylinder. This is the outer cylinder, this is the inner cylinder. Now let's see the inner and outer surfaces of the inner cylinder. Now this particular region will be the outer surface or outer diameter of the inner cylinder, whereas this particular surface will be the inner surface or inner diameter of the inner cylinder. Okay, so that is what we are, that is the concept of compound cylinders, where two cylindrical shells will be placed. And one more thing to be, more important thing to be noted is here actually the inside diameter of the outer cylinder, that is the Note it here. I will repeat one more time. This is the outer diameter of outer cylinder. This is the inner diameter of outer cylinder, and this region is also the outer diameter of the inner cylinder, and this is the inner diameter of the inner cylinder. And here, if you note how it is, how two cylindrical shells are fitted. Actually, the inside diameter of the outer cylinder is smaller than the outside diameter of the inner cylinder. That is, the inside diameter of outer cylinder is smaller than the outside diameter of the inner cylinder. So it is these two cylinders are having a tight fit, or else we can say it is basically shrunk fit. That is, outer cylinder is shrunk fit over the inner cylinder. Okay, the inner diameter of outer cylinder is greater than the outer diameter of the inner cylinder. So if you fit, it will be a very tight fit. So outer cylinder is shrunk fit over the inner cylinder by either heating or cooling process. Okay, that's how the two cylinders are fit. That is, a shrunk fitting takes place in the case of compound cylinders. So after shrunk fitting, basically you cool down the process. You cool down the cylinder itself. After shrunk fitting, either heating or cooling, later on you cool down the cylinder. So once you cool down the cylinder, what happens is, at this junction, of the inner cylinder and outer cylinder, contact pressures will be developed. At this junction, pressures will be developed, and these contact pressures, if you observe, will induce compressive tangential stress in the material of the inner cylinder. The pressures which is generated here will induce compressive tangential stresses in the inner cylinder, whereas it will induce tensile tangential stresses in the material of the outer cylinder. That is the case. If you observe also, it is you can understand, when there is an inner cylinder and we are fitting an outer cylinder which is a very tight fit, then at that junction pressures will be generated. So these pressures will induce a compression. That is, a compressive force or compressive stresses will be induced in the inner cylinder. So this is the direction of the compressive stresses. Then if that is a compressive stress for the inner cylinder, that same stress will also act as will be a tensile stress in the case of a outer cylinder, right? The compressive stress acting on inner cylinder will basically be a tensile stress acting on the outer cylinder. So that is the two different types of stresses that will be induced due to the contact pressures that will be generated at the interface of these inner and outer cylinders. Okay, so so now what happens is, you have fit the two inner as well as outer cylinders. Shrunk fitting takes place, contact pressures are generated, compressive stresses is present in inner cylinder, and tensile stress is present in the outer cylinder. Now you load the compounded cylinder. So you fill the cylinder with fluid at high pressures and all. You fill the fluid tank cylinder with high pressures, some internal pressure will be there for the fluid, so it will have some internal pressure. Then what happens is, so you know how the pressure is acting, right? It is acting against the walls. Internal pressure will be acting against the walls, and the direction of internal pressure will be opposite to the direction of the compressive stresses acting in the inner cylinder, right? So internal pressure is acting opposite to the compressive stresses which are acting on the inner cylinder. So what happens is, when you load the cylinder, due to the internal pressure, the compressive stresses will get relieved. And this internal pressure then further induces the tensile stresses. Whatever compressive stress is there, that will get relieved first. Right? So then it will induce the tensile stresses. So this type of compound cylinder is basically highly useful in resisting higher internal pressures than a single cylinder with same overall dimensions. Okay, so what happens is, if you consider a compound cylinder since there is a additional compressive stresses which are pre-induced in the inner cylinder, you can have higher amount of internal pressures in the cylinder, so that whatever higher pressure is there, first it will it will relieve the compressive stresses which are present, and then it will act on the outer cylinder. So the allowable stress of this entire cylinder will be higher than the internal pressure. So with that value, we can basically determine the dimensions and design the cylinder itself. That's why we use compound cylinder, so that we can pre-stress the cylinder, so that higher internal pressures can be withstanded by the. So next we'll go through the concept, that is the stresses that is generated in compound cylindrical shells. So as I was saying previously, so after shrunk fitting, once you cool down the compound cylinder at the interface, that is at this particular interface, contact pressures will be generated, and due to the contact pressures, if you observe, this is the inner cylinder and this is the outer cylinder, as it is mentioned here. This is the inner and outer cylinder. So due to contact pressures, compressive stresses will be generated in the inner cylinder, and tensile stresses will be generated in the outer cylinder. So this itself is the stress which will be induced, that is pre-stressing, that what is taking place is this. So these are the two different stresses that will be generated, right? And it is also shown here. Compressive stress will be induced in the inner cylinder, and tensile stress will be induced in the outer cylinder. So once the, that is internal pressure, right? It mentioned, once you load the cylinder and there is certain internal pressure acting on the inside of the cylinder, then it will first first reduce or first relieve the compressive stresses which is acting on the inner cylinder. It will first relieve the compressive stresses, and then it will induce the tensile stresses. So this is how higher internal pressures can be permitted in a shell by using the concept of two shells, that is compound cylindrical shells we can use to allow higher internal pressures to be stored inside a cylinder. Okay, so we'll not be going through the entire derivation part of the compound cylindrical shell stresses generated. We'll only go through certain equations which has been used and which will be further used for numerical problems. And this general expression for the tangential stress which we had derived earlier. So this is the tangential stress equation at any radius r. That can be inner radius, outer radius, or the junction radius. And the tangential stress expression can also be obtained from the equation from data handbook from equation number 7.10a. So coming to the next one, so the same tangential stress equation which we previously considered, right? We will simplify that tangential stress equation considering only the internal pressure and considering only the outer pressure. We'll simplify the tangential stress equation by considering only internal pressure by making external pressure equal to 0, and later on consider only external pressure by making internal pressure equal to 0. Okay, so if you consider only internal pressure, then P naught will be equal to 0. P naught will be equal to 0. So and then you can further simplify. You can see Pi di square d naught by d naught square minus di square is a common, so you can take that out. Then it will be 1 plus d naught square by 4r square. And this is the form in which in your data handbook you can see the expression for tangential stress considering only internal pressure. Okay, it is in equation number 7.11a. So this is the expression for tangential stress considering only the internal pressure. That is, if you have to consider the inner surface of the inner cylinder, then only internal pressure you need to take into account. So in such conditions, what will be the final expression that has been derived here? Okay. So next we'll consider only the external pressures. Only the external pressure. So if you consider only the external pressure in the previous tangential stress entire equation, what happens is Pi will be equal to 0. Pi will be equal to 0. So if Pi is equal to 0, then this is the expression which you will get. right? And by rearranging, minus P naught D naught square by D naught square minus Di square is a common, and it will be 1 plus Di square divided by 4R square. At any radius R, you can put R is equal to Ri, or R is equal to R naught, or R is equal to Rc. Rc means that is the junction radius. Okay, so and this is the expression which is given in our design data handbook. This is the final expression that has been given in our data handbook. As per the design data handbook, I think it is not exactly given. Okay, so this is the expression for tangential stress at with considering only the external pressure. So if you have to consider the like say outer surface area of a cylinder, then we may have to consider only the external pressure acting on those cylinders. So in such conditions we can use this particular expression. Okay, only this particular expression we need to take into account, that is the outer surface of the inner cylinder. If you need to take account, then considering the external pressure we can make use of this particular expression. So next we'll go through some of the terminologies that are used with respect to the compound cylinders. I have told you previously, right? That is the inner diameter of the outer cylinder. Inner diameter of the outer cylinder is smaller than the outer diameter of the inner cylinder, right? That is how the shrunk fitting is basically taking place. That is how the shrunk fitting is basically taking place, right? So that's why a tight fit is taking place. So let's see the diameters. D naught is nothing but the outside diameter or outer diameter of the outer cylinder, right? And Dn, which I have considered here, Dn is nothing but that is the inside diameter of the outer cylinder. That is the inside diameter of the outer cylinder, right? How you can see that? This is the inside diameter of the outside cylinder. Then if you note down, Di is nothing but the inside diameter of the inner cylinder. It is the inside diameter of the inner cylinder, and ds is the outside diameter, that is this particular point. This is the outside diameter of the inner cylinder. You can see how the inside diameter of outer cylinder is smaller than the outside diameter of the inner cylinder is. This, due to this difference, basically a shrunk fitting is taking place. Okay, so due to this shrunk fitting, if you consider a mean position, due to this shrunk fitting, then with respect to that position, if you consider the diameter, then that is the diameter dc, that is the diameter of the contact surface with respect to the compound cylinders. That is the diameter of the contacting interface, right? And the pressures generated at that interface is known as the contact pressure, that is pressure pc. And if you also observe, at this particular junction pressures are generated, right? At this particular junction pressures are generated, but this pressure which is generated here, will be external pressure with respect to inner cylinder, right? The pressure generated at this interface or at this junction will be the external pressure with respect to inner cylinder, and the same pressure will also act as an internal pressure with respect to outer cylinder, right? The pressure which is generated here will act as a external pressure with respect to inner cylinder, and the same pressure will act as a internal pressure with respect to the outer cylinder. So considering those two conditions, we will simplify the further equations. So first we will consider the tangential stress equation at the outside diameter of the outer cylinder. That is the tangential stress with respect to the outside diameter of the outer cylinder. That is where I have kept the pointer. So this is the outside diameter of the outer cylinder, right? So R you can substitute as diameter d naught, that is outside diameter of outer cylinder is d naught. So d naught divided by 2 you can substitute, right? And as I already said, the pressure which is generated at this contact will be internal pressure with respect to the outer cylinder. You can understand those things. It will be internal pressure with respect to the outer cylinder. That's why PI will be substituted as PC, that is contact pressure PC. Internal pressure will nothing but be the contact pressure PC, and internal diameter, if you consider, it will be nothing but the contact diameter, contacting diameter. So substituting those expressions in the previous tangential stress for only internal pressure equation which we had derived, right? Previous slide we had derived the expression considering only internal pressure. So into that, if you substitute R value, PI value and DI value, so you will get this expression. You can see d naught will get cancelled, so 1 plus 1 will be 2, so you have to multiply 2 here, right? So this is the final tangential stress equation for outside diameter of the outer cylinder condition, and you can get this equation in data handbook from 7.16b. So next we'll go through other things. So next is the tangential stress we'll consider at the inner diameter of the outer cylinder. We completed outer diameter previously. Now we'll consider inner diameter of the outer cylinder. So if you consider inner diameter, the inner diameter of the outer cylinder we'll consider is the uh, diameter DC, that is contact diameter DC. So R we can substitute as DC divided by 2, right? And internal pressure, I told you, it is nothing but the contact pressures, and the internal diameter which can be substituted as DC, right? So the only change present here will be the radius R. Earlier it was d naught by 2. Here since we are considering inner diameter is nothing but the contact diameter, so DC divided by 2. The same expression, that is internal pressure equation which we derived, into that expression we have to do the substitution, right? This is the final expression which you will get for the tangential stress, and there will be an additional term, that is the Poisson's ratio will be added to this particular equation, and this is the equation for tangential stress at inner diameter of the outer cylinder, which you can get from equation 7.16c from data handbook, right? After that, we completed the outer cylinder, right? We completed the outer cylinder. Now we will consider the inner cylinder. So for tangential stress at the outside diameter of the inner cylinder, So with respect to inner cylinder, DC will be the outside diameter, right? The contact diameter will be the outside diameter for the inner cylinder. So R we can substitute as DC divided by 2, right? And as I have told you, the contact pressures generated at the junction will basically be considered as external pressure with respect to the inner cylinder, because it is acting at the outer surface of the inner cylinder, so it will be considered as external pressure. So we have to consider not Pi here, we have to take P naught. So that will be equal to PC, and the diameter, I told you, it is nothing but the contact diameter DC, right? So here you have to substitute this not in the internal pressure equation. You have to substitute in the simplified expression considering only the external pressures. If you observe the second slide after the stress derivation, we had derived for tangential stress considering only internal pressure and only external pressure. So here we have to substitute with respect to the external pressure equation, right? So R is nothing but DC by 2. So you have to substitute, and this is the final expression which we will get. And okay, so this is the final expression which we will get for the tangential stress at the outer diameter of the inner cylinder, which you can get from equation 7.16b. So similarly, consider tangential stress at the inner diameter of the inner cylinder, where R will be nothing but di by 2. Rest will remain the same, right? So di will get cancelled, and this is the final expression which you will get for tangential stress at the inner diameter of the inner cylinder, right? So next we'll go through similar expressions considering the radial stress. So this is the general expression that has been derived earlier for the case of radial stress, and you can get this expression from equation 7.10b in your data handbook. So the same procedure we'll do which we earlier carried out for tangential stress. Initially we will consider only the internal pressure, this equation will be further used for considering the outer cylinder, and also we'll consider only the internal pressure, and this is the final expression which we will get considering only internal pressure, where we will substitute P naught is equal to 0, and considering only external pressure where Pi will be equal to 0, and this will be the final expression. So we'll further use these equations, that is we'll substitute Di in terms of Dc or Pi in terms of Pc, and use these equations further. So same procedure will carried out. So here considering radial stress at the outside diameter of the outer cylinder, as which was shown earlier, R will be equal to D naught by 2, right? So internal pressure will nothing but the contact pressure, and internal diameter will be nothing but the contact diameter. So substituting R is equal to D naught by 2 into the equation considering only the internal pressure. So this is the final expression we will get. Right, this is the final expression which we will get. If you observe, D naught and D naught gets cancelled, so there is no radial stress at the outside diameter of the outer cylinder. There is no radial stress acting. Now we will consider the radial stress at the inner diameter of the outer cylinder. Inner diameter of the outer cylinder. If you consider inner diameter of the outer cylinder, it is nothing but the contact diameter. So R will be dc divided by 2. Internal pressure will be Pc, and internal diameter will be dc, right? So this can be the final. I think we can further simplify and get the equation for the radial stress at the inner diameter of the outer cylinder, right? So this is the final expression. You can simplify it. If you see this and this gets cancelled, dc square gets cancelled, and sigma R is equal to. So this is the final one, that is the radial stress at the outside diameter of the inner cylinder. So for the outside diameter of inner cylinder, we have to consider the equation, that is the contact pressure Pc will nothing but the external pressure, right? So we consider the equation for radial stress considering only the external pressure. So R will be equal to dc by 2, right? So P naught will be equal to Pc, that is external pressure is nothing but the contact pressure, right? So substituting in the equation for external pressure condition, so you can substitute same thing you will get. So dc square minus di square, and numerator and denominator will get cancelled, and sigma R will be equal to minus Pc. And the last condition remaining, that is the radial stress at the inner diameter of the inner cylinder, where R will be equal to di by 2. When you substitute, you can see here di and di will get cancelled, so 1 minus 1 will be 0. So sigma R will be 0 in the case of inner diameter of the inner cylinder. So these are the different values of radial and tangential stresses at inner and outside diameter of inner cylinder as well as outer cylinder respectively. Thank you everyone.